Okay, so now it's on to question 40. This one will just read: a steel cable has that mass and cross-sectional area. His Young modulus is that when the cable lies on horizontal ground, its length is 40 meters. What's the extension when it's suspended freely from one end and hangs back? So, initially, what I was thinking was of simply using this formula. The Young's modulus equals the force times the area. No, sorry. That's the wrong color as well. Young's modulus equals the stress over strain, and the stress is the force per unit cross-sectional area, and the strain is the extension per unit length. So then we get this, and then if we rearrange, we can get the extension. And we're given all these values, so I was thinking of plugging in the force is going to be the force in the cable if it's hanging. It's got the weight pulling it down, mg, and this is the force acting on the wire, so it's going to be this. This is what I was initially thinking, and then just plugging in all the values. But the reason this method doesn't actually work is because, so I'll draw the wire out over here. Let's say this is the wire, and this is where it's hanging. So at the top, yeah, sure, this is going to be, this will be true. So this part of the wire, the cable, sorry, at the very top, is the mass of the wire below it is mg, is like the total mass. So the force acting at this part through the tension force in this wire at the very top, the cable at the very top, is going to be mg. But it's actually going to decrease as we go down. For instance, down here, let's say it's over here, it's only supporting half the weight. If we're halfway down, it's only supporting half the weight. So the force through the wire is going to be half of what it was up there. So F over here is going to be half that. So obviously, if the force is less, because the cable of Basics law, that's kind of, yeah, the cable of Basics law, which means that the force is proportional to the extension. This part of the wire is going to extend less, and yeah, so this part at the top is going to extend the most, and as we go down, it's going to extend less until we reach all the way at the bottom where it's not supporting any mass below it. So the force there's not going to be any force in the wire, in the cable, sorry. So it's not going to extend at all. So yeah. What I saw a lot of like solutions arguing was that it's kind of, yeah, it's intuitive that because the density of this wire is constant. So I should say, let's say what we'll call m the mass of this section over here, where this is L, like a distance L up the wire. So because the density is constant, we get the mass of the wire is proportional to the distance. These are all constants. Density, the cross-sectional area, the gravitational, what's it called? The G, strength of gravity. Yeah, that means that the force is also proportional because the force is going to be the mass of the cable below. The force at any point in the wire is going to be the mass is going to be the same as the weight of the cable below it, of the section of cable below it. Oh, sorry, that's not G there. So it's going to be rho L A G. So yeah, the force is proportional to the length. And yeah, what did they argue? Oh yeah, they argued that this setup is equivalent to if we could just say that the average force through the wire is going to be, because the force is proportional, so it's max over here at the very top, and it's minimum down here. So what a lot of solutions you see online, they argue, is that it goes from mg, like the full mass, which we'll call, let's say, I don't know, MO. So this should all be MO. So MOG over here down to 0. That's what F varies between, and it varies linearly with length. So that means halfway, like its average is going to be halfway along. That's going to be half MOG. That's going to be the average force over distance. So yeah, anyways, that's well off. They just use that and then plug that into this formula over here. So instead of writing mg, half mog, and yeah, they got the right answer. But I don't know, it's not very like, you just have to kind of assume that you can use the average force over the length. Like, yeah, I don't know how to explain it, but it's not like why it's not sass. But yeah, if you understand, you understand. Like, it's not. I don't think it's a very satisfying explanation. So yeah, we went after a deeper explanation and got there in the end using Chat. Like, I don't think it's bad to use ChatGPT in these sorts of AI, as long as, like, because it can really help. It can, like, just like, it's pretty much like searching up on Google, but just quicker, and you get more specific results. But you just really need to check you understand, and not just like mindlessly copy down what they say, and like really think through it. So I'll show you the method to solving this. So the way we're going to have to use calculus for this. So the way it works is we're going to start by thinking, we're going to split up. We've got this long cable. This is a cable. And we're going to split it up into a bunch of little discs. And the reason why we'll do that, so there's a disc there, let's say, and then there's discs all the way around. There's another disc there. So we split them up into these tiny discs with width, let's call it DL. We'll say L is the height of the disc from the bottom of the wire, and DL is the width of the discs. And yeah, so, and then the reason we split them up into these discs is because the force, as we've seen before, like, or as we understand, yeah, as I explained before, the force varies proportionally with L. So as L increases, what was the form we got? F. Can't remember what we got, but oh yeah, it was this. That the force. Let's say this is the tension force. We're just going to imagine the what's it called? Yeah. So we're going to imagine the forces on this little disc. So we'll say F is the force. So yeah. Anyways, sorry. So the reason we split it up into these small discs is because the height, like, as DL goes to 0, the force throughout, there's no height change. So from the top to the bottom, so like between here, as this distance shrinks, the force throughout the disc stays constant. Because remember, the force only varies with this, with L, with this vertical height. So as DL shrinks, as this goes to 0, yeah, this is going to be the same over here as it is down here, as it is down there, So it's going to be the same all throughout this disc. I hope that makes sense. So we're gonna be thinking. We always got to have in the back of our mind that we're going to be thinking about this as the width of the disc goes to 0. So anyway, so let's look at the forces. So the forces are going to be balanced because this disc is not going to be moving anywhere. Well, once it's extended. So yeah. So we need to think about the small. So we'll also say that this disc extends by a small amount when it's hung vertically. It extends by even smaller than DL, dx. It's going to extend by a tiny amount dx. So the DL is the original. Like, if we just lay it horizontally like that, DL would be this part of width, and then dx is if we get this and then rotate it 90 degrees. And hang it vertically, dx is how much that part extends. So in that case, this would probably be dx. This is dx over here. But anyways, that's just to show you. So, let's see. So as dl goes to 0. So anyways, so we're going to think about the forces. Think about forces on green disk. So we've got the tension force pulling up from the rest of the wire, from the rest of the cable. But we've also got this, because if we imagine treating the rest of this cable that's below it, it's like one object. Well, the rest of this cable is going to weigh. It's going to weigh a mass. It's going to weigh ml, where we say ml is its mass, g. Okay, so that's going to be, and then the force. So obviously it's not moving, so that's going to be. Sorry. So this force is going to be mlg, and then obviously it's not moving, so there's got to be another force upwards that's also mlg, and that's the force from the green disk. That's like that's the force the tension force provided by the green disk. And because of Newton's third law, we know that this yellow section puts the same force onto the green disk as the green disk puts on the yellow section. So if we look at the green disk now, we can say that it's also going to have as well as the upwards force F, it's also going to experience the tension from the cable above it. It's also going to experience the downwards force mlg. And now at this point, you might say we also have to think about the mass of the. We also have to think about the mass of like this disk itself, right? But the thing is, we don't actually, because as d, like this is where it gets like my reasoning gets very flimsy, like, and you'll get this all the time when you're working with like infinitesimals and trying to like build up your own like differential equation. Sorry, like the reasoning becomes very flimsy, and like it's only justified by some math that I've got no idea what the justification is. But anyways, so yeah, I mean you can include it, but then you'll end up excluding it at some point, like through other flimsy arguments. So you might argue, why don't we include the mass, like let's call it dm, the weight of this small green disk as well? Well, the reason we say it is because as dl goes to 0, dm also goes to 0. So this becomes very this becomes like very relevant. Even though we don't ignore dx, because even though that also goes to 0, we don't ignore as dl goes to 0. We just do ignore dm. I mean, but we can include it just to show you that, like, So anyways, so by saying forces are balanced, what we get is F equals dmg plus mlg, which is going to be dm plus ml all times by g. So we have an expression for ml. So that's going to be simply this length L times the cross-sectional area to get the volume times the density, and then dm is going to be dl plus dx. We can say it doesn't really matter, we could just write dl as well and pretend that the extended part has got no mass. These are some very strange assumptions, but anyway, anyways, so we'll include that as well, times a rho. So what we end up getting is F equals, what's that, dl plus dx plus L times by a rho g. Okay, And now let's think more about so what we know is that the tension force in this green section is F, and because of Hooke's law, we know that this thing obeys Hooke's law. We know that it's going to be K is going to be some constant. We'll call it the spring constant times the extension of this section, which is dx. So we get F equals K dx. Where K, I can't remember. This is also equivalent to using that stress over strain idea, which says that we end up getting. No, sorry. It's so to derive that, I always remember it as Young's modulus equals stress over strain, which is FL over. Sorry. Anyway, wait. Let me just reword this. So I'm just doing this now to find. Now I want to find what K is in terms of the Young's modulus, because obviously we don't have the spring constant. So the way I'll do that is by rederive. Like there's a formula for it, but I forgot on it, so I'm just going to rederive it. So like I can say, just rederiving it over here, just quickly. So we know generally F equals Kx, but also Young's modulus equals stress over strain. Stress is force over area. Strain is extension over original length. So therefore E equals FL over AX. So that means F equals EA over LX. And then comparing these two, which have to be true both at the same time always, K equals EA over L. Okay, so that means the spring constant is the Young's modulus times the cross-sectional area of the original length. So what that means in our case is that we got the Young modulus times the cross-sectional area over the original length, which is dl dx. So yeah, that's what we get. And then here's where the flimsy reasoning comes in. So I'll just delete that to get rid of that. So plugging this into this expression over here, we get EA dx over dl equals dl plus dx plus L times by A rho G. And I'll tell you now, what I'm trying to get is an expression for dx in terms of dl. And I can explain, you'll see more why, but I'll just tell you now that that's my goal. So yeah, here we go. So dx is going to be, that becomes dl squared plus dx times by dl, dang it, plus L times dl times by A rho G. Okay, and then here's where the flimsy reasoning comes in. When we're coming up with these differential equations, whenever we have two differentials multiplied by each other, as we do over here, this is what I've just, like, I'm not sure if there are any exceptions to this rule. I've only done it to A-level maths or A-level further maths. I'm not sure if there are any exceptions, but what it seems like is that whenever we have two differentials, and we're ready to start integrating, we just ignore them because these go to zero much more rapidly than the differentials do. So they become we can ignore these. So what we can say is that, I'll just write it here, as dx goes to 0, ignore these terms because they vanish much faster. See, this is the flimsy reason. This is why you need to study some high-level maths to be able to understand this. I hope maybe it's not too high level, but that's what I'm guessing. So then we get dx equals L A rho G dl. Is that it? I hope that's it. Oh no, I forgot to bring over the EA, so this is over EA. So over EA which is L rho, no, which is rho G over E L dl. And now this is what we do. To find the total extension, we basically have to sum up all the small extensions going from the disk. So I'll just write it here. For all disks starting at the bottom of the cable to the top. Just write that in words. And then we also need to take in the limit as what is it? The width of these disks goes to 0 to make this approximation that f is constant throughout the height of this disk. We need to make that more accurate, we need to take the limit. And then basically what by like some magic, which the mathematicians don't understand, but I don't, this becomes the integral of dx going from L, not going from x, going from L equals 0, from the very bottom, going from the disks at this very bottom part, going from these disks at the very bottom, to L equals, let's call the actual length of the cable L going to the disk at the very top. So yeah. And then if we substitute this in, we get rho G and E are all constants. We get this L dl, and that's just a simple integral to get. So the total extension becomes rho G over E times by half L squared between L and 0. So that's rho G L squared over 2E. And then that's the total extension. So what we get finally is the actual length. The new extended length is going to be the original length plus the extension, which is going to be L plus rho G L squared over 2E. Okay, now we get to, so that was the reasoning. See, the reasoning is pretty hard, which is why I don't want to put any numbers in until we get to a final formula, because otherwise the numbers just distract us. So hopefully that made sense, more sense than any other explanations out there. Now we'll do the easy part, but the part where I'll probably make the most mistakes, plugging in numbers. So we got the density. So we weren't actually given the density, but we were given the mass and the cross-sectional area and the length. So the density is the mass. We'll call big M the actual mass of it over the volume, which is the mass over the cross-sectional area times that actual length. So that means this shouldn't be there. Therefore, L prime is going to be L plus MGL over 2AE. So yeah, we can rewrite it even more nicely as 1 plus mg over 2AE all times by L. And now we can plug stuff in. So we get the new length. Oh no, we don't even want to find the new length, we just want to find the extension. So delta x equals mg over 2AE, which is what? 64 kilograms times 10 newtons per kilogram over 2 times the cross-sectional area, which is 2 times 10 to the minus 4 meters squared. Times E, which is 2 times 10 to the 11 Pascal. What is it actually? Yeah, pascals. Okay, so anyways, I hope you see the use in like using algebra, like giving everything symbols. As long as you make a note of it and you're clear about what your symbols are, it's a very good idea, because things get less messy and with like numbers all over the place, and then just doing the simplification at the very, very end. Because then you can also follow your working easily, because you're not confused with which number represented a what and all of that. So I'd highly recommend doing workings at the very end. So here we go. Just simplifying now. The units, I just write the units in just to check that everything's in standard units. And once they are, I know that the whatever I'm trying to find will also be in standard units. This is going to be in meters now, I know. So that's going to be 8 times 10 to the 7. That's delta x is going to be 8 times 10 to the minus 6 meters. Let's hope that's an option. Yeah. That's an option, but for some reason I don't think it's right. I think other people got different answers. But anyways, I'll come back and check. Oh wait, I'll come back and confirm whether that is right. In fact, I confirmed that I was wrong, and that's actually because I forgot to write. I'll do it in red just to check. So this is wrong. I forgot to write L over there. So this should actually be L. So it should, I forgot to times by the 40 meters. So timesing this by 40. So I can turn that cross into times by 40 meters. So the actual answer is delta x equals, what's that? That's 320 times 10 to the minus 6 meters, which is 3.2 times 10 to the minus 4 meters, which is G, which is the actual answer. That's not the actual answer. Okay, there we go. Got it right.